Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today video we would like to tackle the question of quiz number 2 for section 4. So the question was taken from our handout number 5, question number 15 as shown here. Okay, let's read the question together and let's try to underline the important wording which might affect the way we're going to solve this problem. The question states that 2 infinitely long. So I'm going to underline the word infinitely long. Coaxial cylinder surfaces R equal to A and R equal to B, where B is much greater than A. Carry surface charge density. Okay, so we are dealing with surface charge noted as rho subscript as A and rho subscript as B respectively. Determine E everywhere. So let's look into question number 1 first. Okay, find E everywhere. So the E here indicate that we should try to determine the electric field intensity due to the surface charge. Okay, and the surface charge is in a coaxial cylinder that is infinitely long. Okay, that should be the summary of our problem. So let's try to list all the important statement that we can extract from this particular question. Question number 15 of handout number 5. That should be the quiz number 2 question. So infinitely long. Okay, that should be one important word. Okay, another should be surface charge. Okay, we want to determine the electric field intensity. So that should be the goal of this problem, finding electric field intensity due to the infinitely long coaxial structure that dealing with the surface charge. Okay, so when we remember in our previous lecture, if we have a charge and we want to determine the electric field, there are two methods that we can adopt, either Coulomb's law or Gauss law. Okay, that should be the typical step that we can use to find the electric field whenever we have source stationary charge. And if given the choice, we would like to adopt Gauss' law compared to Coulomb's law due to the reason Gauss' law is much simpler in the process of solving. So there are certain criteria that we can use Gauss' law, and one of the criteria of the source should be infinitely long. Okay, so due to this argument, the cylinder is infinitely long. Therefore, this problem can be solved by using Gauss' law. Okay, that's the reason why the question state clearly regarding the nature of our cylinder, which is infinitely long. So let's draw this particular structure. So we have inner cylinder. Okay, that should be the first cylinder. So coaxial mean that the cylinder, both cylinders having the same axis. That's what meant by coaxial. Coaxial meaning that both cylinder are having the same axis. So meaning that the axis of these two cylinders are common, meaning they're having the same axis. So let's draw it clearly. Okay, there are our two cylinders. Okay, so one is having a radius A. Another cylinder is having a radius B. Because both cylinders are infinite, I'm going to add this extra information by noted this dotted line. So this dotted line to inform me that this structure are infinitely long. Okay, that's what is meant to me. Okay, that should be the structure itself. And then regarding the source, there are two surface charge. One is on the inner cylinder denoted as rho SA. Another one is located on the outer cylinder rho SB. Okay, so that should be our diagram of the problem. So now, first when we dealing with Gauss law, always the first thing that we always conclude is regarding the coordinate system. Since the structure of this problem is a cylinder, therefore logically again, I should use cylindrical coordinate. Then from the diagram itself, we can see there are three distinct regions. What I'm trying to say here, I can split the region in three sections. One section is inside the inner cylinder. That should be my section number one. The second section is between the inner cylinder and the outer cylinder. That I'm going to define as my region number two. And the last region or section will be the region outside the outer cylinder. I'm going to denote as region number three. Okay, so the way I'm defining the region based on the actual problem. Okay, in this region we can see there are three distinct regions as shown here. So therefore, I'm labeling three different regions. Okay, so I'm going to first try to solve E in the region number one. Okay, I'm going to denote in region number one using which method? Gauss law. Okay, let's draw it in this. So this is the part of the inner cylinder that I can't see. Okay, so that should be, so I'm going to find the E inside region number one. So I'm going to define it to be, let's say, here. Okay, that should be my position of the E in region number. It can be anywhere provided in region number one. So I draw it here. So then, based on Gauss law, after defining the position of the D, I have to build the sensor, which we call it to be Gaussian profile. And the Gaussian profile should agree with the selected coordinate system that we use in this problem, which is cylindrical coordinate. Therefore, the Gaussian must also be a cylindrical structure. Okay, so let's draw the Gaussian. So my Gaussian now in 3D representation going to be like this. Okay, so that should be my Gaussian, and you can see the Gaussian structure also having the same axis as our inner cylinder and outer cylinder, meaning they are actually having the same axis. And the Gaussian, I'm going to denote something that not fixed. I'm going to give it as R, because we can see this position of D is not fixed. It can be anywhere provided in region number one. But I'm going to make the length of my Gaussian to be fixed, because this is our sensor. Yeah? So therefore, that should be my Gaussian profile. Step number one, step number three. Step number one, selection of coordinate system. Step number two, after identifying the logical regions in our problem, I'm going to define clearly where my D. So therefore, I'm going to build my Gaussian step number three. So now this is what we're going to end after step number three. And you see, for step number three, the R must always be smaller than A. Okay, that should be what should agree between our definition of region and what happened to the Gaussian profile. Yes? There must be a tally between them. So to make this matter easy, I'm going to draw in 2D. Okay, 2D mean that for region number 1, what we have, this is the inner cylinder. What is our radius from the plan view? This should be A. Okay, I'm going to look from the top now. And then we already defined just now, this is our D location. Then we built the Gaussian, which is a cylinder, but looking from the top, it appears to be as such. And then this Gaussian having the radius R. Okay, and then we know from the diagram, the charge is located where? The charge is residing on the surface of the inner cylinder, which is rho S A. So that should be the plan view of this diagram, looking from the top, just to make the matter easier to be interpreted. Now, okay, I'm going to continue now. So now we are doing the actual Gauss law, step number 4, d dot ds equal to Q enclosed. And then from our previous discussion, based on the same structure before, this Gaussian can be split into 3 different surfaces. The top surface of this cylinder is surface number 1, as mentioned in the previous lecture. Then the curved surface we define to be surface number 2, and then the bottom surface of the cylinder, surface number 3. But we know, due to the nature of infinitely long, the D that exists in this structure will only be consist of component R, where component phi and component Z will be neglected, because infinitely has been proven by our experience regarding infinitely long line charge. The E or the D that been produced by that source will only consist of the R component of cylindrical coordinate. So therefore, we're going straight away to use that argument here by only saying that the component of surface that should be considered is the curved surface, surface number 2, giving the solution to be dr 2 pi r and h. See, the radius is r and the length of the Gaussian surface is h. Therefore, 2 pi rh, that should be the left hand side. So now let's consider the charge confined by the Gaussian. So this is our Gaussian. So is there any charge that residing inside this region? From the observation, what we can see, the charge actually only appear to be on this surface of radius r equal to a. But inside it, there's no charge. Therefore, as we can see from the diagram, there should be no charge in this region. Correct? Therefore, the solution should be equal to 0. So therefore, our D region of 1 is simply said equal to 0. But the question asks for the E, remember? And D equal to epsilon naught E, because we are assuming the medium to be free space. Therefore, our E1 will give us the same result here, also equal to 0. So that should be the first solution of region number 1. Okay, so let's repeat now. I'm going to create a structure now. So this should be now dividing to the second region now. So region number 2. Okay, region number 2. So where's our region number 2? As you can see now, region number 2 should be in this particular position. Okay, or anywhere between A and B. So therefore, our Gaussian, as you can see here, the structure should be extended covering this particular position. So what we can see on the plan view now, okay, I'm going to draw based on the plan view from the top. So first I'm going to see this is my outer cylinder, okay, and then I'm going to have inner cylinder. Okay, I'm going to make it clear, this is my A and this is my B. Okay, and then the charge that exists in this particular problem going to be first rho SA and then rho SB. Okay, so but what we're going to say now, the position of our D should be between A and B. Okay, so now we are saying that our R now should be A smaller than R smaller than B. That should be the definition of region number 2. Why? Because this position is between R equal to A and R equal to B. Okay, so therefore that should be our definition of region number 2. And then we're going to draw the cylinder. So we're going to see from the top is going to be as such, and then this particular black surface having radius R. Okay, that should be our logical Gaussian structure that we should create. It's similar to this one, but the only difference that the position of our radius now of the cylinder Gaussian is between A and B. So that's the only difference. Other than that, exactly the same as the first Gaussian, okay, where the height still h. Okay, the only difference now, the radius of this cylinder Gaussian is located between R equal to A and R equal to B. So that's what we're going to observe from the top view. Okay, done that, let's do the mathematics. So similar, I'm going to repeat now the steps. D dot ds equal to Q enclosed. And then we know that this is repetitive now. So what we already saw for the previous structure should be applicable here. So it should be dr 2 pi rh, because remember, this side of the mathematics always refer to the surface of the Gaussian, the black cylinder. So therefore R, okay, and then but the R here and the R here, they are not the same. Remember that these are for region number 1 and these are for region number 2. So please don't confuse, even though we are using the same symbol, but these are based on this particular column. So this nothing to do with this column. This done already. This is R that we define for region number 1 is only true for region number 1. Okay, that should be the case. So let's do the mathematics. Now the charge. Can we see any charge inside this Gaussian? Yes, we can see one charge, which is the charge that located on the cylinder of R equal to A, correct? How about the charge outside here? Is the charge there, but not should be taken into this calculation. Why? Because the word enclosed. Remember, the word enclosed here should be defined as the charge that confined within the Gaussian structure. And in this case, we can see the charge is located on R equal to A. So therefore, what type of charge that we are dealing here? Surface charge, good, should be rho s ds. Okay, that should be the model for surface charge. And then remember, this mathematics must always based on the charge sample, and the charge sample, as you can see, is here. Okay, so therefore the radius now is fixed. What should be the radius of this sample charge? A. So therefore this ds should be substituted with A d phi dz. Not R d phi dz, yeah? A d phi dz. Why? Because the sample must represent the sample on this diagram. this sample is residing where? Yes, on the surface of radius r equal to a. Therefore, I'm changing the r to become a because fixed. Because the sample only located at r equal to a. And when you solve the mathematics here, what you're going to have should be rho as a, because the charge here is rho as a, should be 2 pi a h. Okay, that should be the solution after the integration. And then what we can do, we can simplify the mathematics. I'm going to make it easier by saying D2 now. You can see indicate electric field density in region number 2 should be equal to rho as a divide with r, in which direction? R directions. Because the 2 pi h can be cancelled out, because they are having the same 2 pi h on the left and also 2 pi h on the right. So we can cancel that. And the E, remember the E should be equal to d over epsilon naught, because we are dealing with free space, should be equal to rho as a divide with epsilon naught r in r direction. That should be our second solutions. Okay, let's do the last one, because the question asks for all regions. So I'm going to go for the last one now. Okay, so therefore all region, so be the last one should be region number 3. Okay, so region number 3. So let's draw the plan structure. It's similar to the one for region number 2. I'm going to draw it. So first the outer cylinder, then the inner cylinder. So here radius A, and then this one should be radius B. So rho as A should be charged here, and rho as B should be the charge on the outer cylinder. So now what we are going to find the D in region number 3 should be here. So that should be our D region number 3. So it can be anywhere in this region. Okay, so I'm going to build my Gaussians from the plan view. We're going to see a circle, actually a cylinder, remember, a cylinder. So now the radius we're going to define to be r, and we're going to say for region number 3, r always be greater than p. Okay, done. And then if you solve the mathematics now, so Gauss law state that d dot ds equal to q enclosed. Okay, so now based on experience after solving a lot of problem, so we know the left hand side of the Gauss law should end with dr 2 pi rh. And remember the r here is true for this condition, r greater than b, nothing to do with the r that we defined previously. And based on our q enclosed, what we can see, so Gaussian is here, and from this simple diagram we can see there are two surface charge inside the Gaussian. One is here, another one is here. Okay, so this should be the dq 1, this should be the dq 2, and now what should end? So should be equal to dq1 plus dq2. Okay, so then when you solve the mathematics, should be equal to rho as a 2 pi ah, that should be of the inner cylinder, plus rho as b 2 pi bh. Okay, because that is what this is just mathematics. I think you all can see. So now if I want to simplify the mathematics for region number 3, D3 now should equal to rho S A, correct, plus rho S B, all divided with what? Divide with R. And which directions? R directions. Okay? And then if we want to find the E, and E for region number 3 should be equal to D3 divided with epsilon naught. That should be our solution. Okay, done already for question number 1 of our quiz 2. You can see how easy. It's not that difficult. Okay, so that's done already. So we have solved for this particular question, determine E everywhere. We can see there are 3 different regions, 1, 2, and 3. Alhamdulillah, we have solved for all these 3 cases, 3 regions. And now let's do for the second part of the question. What must be the relation between A and B in order that the E vanish, becoming 0 for R greater than B? So now the question focused specifically for region number 3. So what happened when in region number 3 that the E is becoming 0? What should be the relationship between A and B? So what we should do, okay, for number 2 now, I'm just going to use our solution that we have solved. Okay, so I'm going for go number 2 now. Okay, much better. Okay, for E becoming 0 in region 3, okay, so the mathematics that E3 must be state equal to what here? 0. Okay, so we have solved for E3, and we know that E3 is equal to what? Rho SA A plus rho SB B, all divided with what here? Epsilon naught R equal to 0. I'm just focusing on the magnitude, ignoring the direction. So now the question asks what should be the relationship between A and B. So finally what we can conclude based on the mathematics again. Okay, therefore what should be A? A should be equal to negative rho SB divided with rho SA multiply with B. So that should be the relationship between A and B. Correct? We just multiply with 0 and then shift the second part of the mathematics to the right and then divide with the rho SA. So that should be our final solution. So therefore, we have completed solving question of quiz number 2. So you can see it's very simple, provided you use the basic concept rather than memorizing the solution. Anything that we do, there must be a reason, must be based on the factual law, factual concept, not what we think, what we rasa. Okay, with that, thank you very much. See you in my next lecture. Assalamualaikum warahmatullahi wabarakatuh, and thank you.